Hi, it's thermoelectric generator time again. Those pesky devices that, well, I've done a debunking video on this before. You might remember this one way back, the Matrix-powered smartwatch, for example, where I ran the numbers on that one. Never charge your smartwatch again because it's got a peltier device in it. It's got a thermoelectric generator, one of these Seebeck effect devices, and oh, look, isn't it wonderful? And well, it's just nah. It's a gimmick, as I showed in my video. Now, this video comes about because there's a ton of misconceptions about thermoelectric generator devices, and every time somebody reads a press release for them, or in this particular case, we're going to talk about a scientific paper, extolling the virtues of how they're going to, power smart wearable devices, the Internet of Things, and all this sort of stuff. There's so much misconception out there, so I thought it's worthy to do a video. Now, this one comes as a response to one of my favorite YouTubers out there at the moment, Anton Pretrov from What to Math, and I'll link in Anton's page here. He's on Odyssey as well, so definitely subscribe to him and the EEVblog down on Odyssey. I think I've hit 60,000 subscribers now. Yeah. Anyway, really, I'm telling you, do yourself a favor and check out his channel. So this is kind of like a shout out video too for one of my favorite YouTubers, mostly like astronomy, space related stuff, but in this particular case, any type of scientific research. What he takes is like the latest scientific news, and he links to the papers, and he looks through the papers and explains the papers, gives his take on it, and all that sort of stuff. And it's absolutely fantastic. Probably one of the only channels at the moment that I watch like every single video. Anton talks about this paper here in Scientific Advances, high performance wearable thermoelectric generator with self-healing, recycling, and Lego-like configuring capabilities. All the authors there, and it's fairly recent. Thermoelectric generators are an excellent candidate for powering wearable electronics and the Internet of Things. Groan. Yeah, half my audience just groaned. Due to their capability of directly converting heat to electrical energy. Here we report a high-performance wearable TEG, which is a thermoelectric generator, with superior stretchability, self-healing, recycling, and Lego-like configurability by combining modular thermoelectric chips, dynamic, covalent polyamine, yeah, and flowable liquid metal. Oh, Terminator. Electrical wiring, this is where it starts. Electrical wiring in a mechanical architecture of soft motherboard rigid. They're basically talking about flex. And not flex PCB in this case. It's a different type of material. But anyway, won't get into the details. Anyway, they reckon, yeah, it's going to have a wide range of applications and Internet of Things and everything. And, well, no. Sorry, it's not. Sorry to burst your bubble. Now look, this may actually be like a really good innovation. It sounds really cool. It's like a flexible thing. As you can see here, they've developed this flexible prototype that can sit on the skin. So it's got a self-healing thing so that when you got it on your body, it's going to bend all around the place. But basically stick it on your body and it converts the warm body temperature, hopefully to, roughly 37 degrees Celsius, none of that Fahrenheit rubbish, and whatever the ambient temperature is here. But unfortunately, if it happens to be like 37 degrees outside and matches your body temperature, well, you're going to get zero out of it. But anyway, yeah, if you've got a cooler environment than your skin, then it's going to generate some level of power. So anyway, they claim that this is like better output capability, and of course it's self-healing, so it can't damage itself when it flexes and all sorts of stuff like that. Right, very cool. So it's probably a really good advance, but is it practical? So we're going to run the numbers. How the human body, yes, it generates like hundreds of watts. Like just sitting here, I'm like 150 watts of power, something like that. I'm dissipating that sort of, power level. So there's lots of power there to be harvested for these types of thermoelectric generators. But are they going to be practical? And I've already told you the answer. And the other thing in the videos, Anton talks about energy when he's actually referring to voltage or power. And I've actually done a video on this, I'll link it in down below as well, where I explain the difference between voltage, power, and energy. And a lot of people get this in the industry, or I'm even guilty of like using the wrong terminology myself. It just, rattle off the top of my head and I say energy when I mean power or vice versa. So anyway, it's just really easy to misspeak on voltage, power, and energy. A record high open circuit voltage among flexible ones, 1 volt per square centimeter. And here's where a lot of people in all sorts of industries, when they're talking about these thermoelectric generators, when they're talking about solar cells, they're talking about other energy harvesting devices, is that they think that, oh, it generates a volt. Well, my Intel processor works at 0.9 volts or something. It can power an Intel processor. Well, no, unfortunately, it can't. You've got to watch this video. We'll go through the calculations shortly. Okay, you might be able to... the thing about these is that they are actually modular, and you can actually string them together. We'll have a look at the photo in a minute. But yeah, you can like string a couple of these in series, and you can get higher voltages. So when you're talking about voltage like this, you have to talk about like voltage in terms of, right, that's the minimum amount of voltage required to actually do some work on electronics. When you like anything under 0.5 volts is basically not usable with modern electronics. It's the thing, you can't start switching on silicon gates and things like that. There are energy harvesting chips, and those energy harvesting chips, they might require like a threshold voltage of like 0.5 volts to start up, for example, to start up a DC to DC converter, so that then they convert those voltages to higher voltages. And if you're talking about like a DC to DC converter that starts at 0.5 volts, and you might want to boost it to say 3.3 volts, which is a typical voltage to run, you know, modern electronics with, for example, then, well, those DC to DC converters, they're not very efficient. They take their own power and all sorts of stuff. So it becomes a bit useless when your converter itself actually takes more power than the device you're trying to actually power. And we can actually start having lookers for some energy harvesting chips here, and some of them can actually work down to very low voltages, like, you know, tens of millivolts and stuff like that. And if you go to analog devices here, they actually tell you boost converters that operate from as little as 20 millivolts. But there's a trap. They can operate down to that, but they can't start up at that sort of voltage. So, you know, there's different energy harvesting chips here. Let's just have a look at this one, ultra low power energy harvesting. So it can work down to really low voltages. Yeah, it can operate from 80 millivolts to 3.3 volts input, but the problem is its startup voltage needs to be 380 millivolts minimum. So, you know, energy harvesting is a thing. You can actually get specialized chips to actually do this sort of stuff. So we're actually going to have a look at the numbers and see what we can actually pull out of these new whiz-bang devices. But the problem is, okay, you don't even have to read further than the abstract to know you've already come a gutter. A record high open circuit voltage, first problem, open circuit voltage. That's not under load, that's open circuit voltage. And we'll look at the PV curves, the power versus voltage curves, in a sec. Is 1 volt per square centimeter at a temperature difference of 95 Kelvin. That's 95 degrees. Temperature difference. If you've got a 95 degrees temperature difference between your skin and the environment, you're probably dead. So yeah, you're going to come against us. So right there, we don't even need to read further than that to know, well, yeah, this is not great. So here's some actual performance curves and data provided in that article we've linked in down below. And this is how they'll typically characterize and test prototypes like this. They'll have a heater down the bottom, and they'll have the cold junction on top. They'll have the, you know, and then the ambient temperature out there, and they'll put a load on it and a voltmeter, and they'll get some performance curves on there. And I won't go into how peltier devices work and the Seebeck effect and all that. I've done that in the previous video. But already, yeah, let's look at P out. That's power output here. Microwatts per square centimeter. So let's work with the 1 square centimeter thing, which they show on the finger, in that, you know, that's what they're hyping up as can potentially power these, you know, wearable devices and smartwatches and things like that. We're talking like 10 microwatts. 10 microwatts. But what we want over here, here's your kicker, okay? Here's what's called a PV curve, and you'll get these for these thermoelectric generator peltier devices. You also get them for solar cells and stuff like that. And they typically have a response, or at least the peltiers do. Solar ones look a little bit different. They're sort of more linear and then sort of taper off at the end. But this is a typical curve for a thermoelectric generator like this. So it's power output in microwatts per square centimeters versus the load voltage, the output voltage, which is also across the load if you have one, of millivolts per square centimeters. And sure enough, it can get close to a volt. So I'll give them that. In the article, it says that they get, basically, this is where they're claiming, big headline abstract in their thing, says we can get 1 volt out at 93 Kelvin difference or whatever it was. Yeah, sure enough. I don't like how they did these colors. They should have chosen different colors. But anyway, there's the curve. There it is. Okay? But, as I said, open circuit voltage. You're not powering any load at all. Now, with any solar cell or thermoelectric generator like this, you'll have what's called as a maximum power point, an MPP. And a lot of these energy harvesting chips will actually have maximum power point trackers. And you may have actually heard about those for your home solar systems and things like that. It's more efficient. It'll actually try and track. I won't explain the concept, but basically it tries to operate around this maximum performance. Right at the top of this curve here, this is where you're going to get your maximum power output. So as you increase the voltage like this, the available power actually drops. And here it is, the power output. At 1 volt, you get no power. Zero power out of this thing. So yeah, you're not going to get your 1 volt. But hey, look at this, you might get 500 millivolts, and as we saw, you can get energy harvesting chips that can do this, and you start to get in the realm where it can turn on PN junctions and do useful work and stuff like that. So it's possible, but once again, the power output, 18 microwatts. But again, the kicker, at 93 Kelvin. Okay, that's the point where you're dead. So let's look at, say, your body's at 37 degrees. Let's just assume, you know, it's all perfect. It's 37 degrees. There's no other losses on one side of the peltier device, and your room temperature 20 degrees on the other. So you've got like a 17 degrees difference. So here's our first grey curve here, okay, because this is our last blue one. This is our first grey. So that would correspond to your 31 Kelvin here, okay? So 31 degrees. So you've only got like a 6 degree difference. So you're freezing, right? It's 6 degrees. Don't know what that is in bloody Fahrenheit for you Yanks, but that's all right. 6 degrees. Jeez, freezing. Never get 6 degrees here in Sydney. Nah. So right off the bat, even though you're freezing your ass off, you're only going to get 2 microwatts at under 200 millivolts. And that's not enough really to start up. You know, they start talking 300 to 500 millivolts start up for any sort of energy harvesting thing. It's not going to power anything directly. But the thing is, you can put these in series, okay? So yeah, no worries, right? But yeah, right off the bat, when we're talking about this little thing here on your finger, even if you strung a couple of these in series, each one, even at like you're freezing your ass off, you still only get, based on their actual measured data, you're still only getting a maximum of 2 microwatts per square centimeter. So you string enough of them together to get a high enough voltage to make it useful. And yeah, you're still only going to get 2, 4, 6, 8, you're down in the order of 10 microwatts. So what can 10 microwatts power? Well, let's go to the bench quickly and we'll measure the power of something like this. So how much power does something like this ultra low power solar powered FX260 calculator? I've done a review on this and an experiments video. I might have to link, geez, how many videos am I linking in? Anyway, there you go. There's a little shot inside. We've got like a solar cell. There's no battery whatsoever. It's powered just from that. So I've hooked in some wires and we can see that this is the voltage measurement coming from the solar cell, about 2.7 volts, give or take. And then we can also measure the current as well, and here it is. Can't really make heads or tails of that, but if we put on our trend chart, check it out, I can clear the readings, and there you go, just sitting there at 2.7 volts. So, you know, we're talking like 30 microamps, something like that. 30 microamps times 2.7 volts, put in engineering notation, about 81 microwatts for this little tiny solar power calculator. But of course, it's operating at a higher voltage. It can actually operate lower than that. And to demonstrate that, let's actually cover the solar cell and you'll see the voltage drop. Let's get it to a point where, yeah, around about a volt. Once it gets to about 0.8, you'll start to see those digits fade a bit. Can operate down at 0.8. That's kind of like typical of this sort of, you know, processor ASIC node, as they call them, at the silicon level, you know, 0.8, under that, it's going to start to really fade. Geez, it must be getting some light through there. So there you go, 0.8 volts. It's barely on. It still actually does work, and we can actually rescale that. There you go, you know, 2 or 3 microamps, something like that. Not too bad. And there's actually a interesting thing here. You'll notice I've put all 8s there on the display, so we're turning on all the segments, and you'll notice that it's not really using any more than that sort of like, you know, 2.5 microamps. It really doesn't change. I'll clear it. There you go, and it doesn't use any less power. But if we go back to our full voltage, and we'll auto scale that, okay, so we're back to 10 microamps now at 2.7 volts. If I do, or if I turn on all 8s on the display down there, you'll notice that it's actually drawing more power now because it's got all the segments. Yet it doesn't do that at about, you know, it doesn't draw more with having more LCD segments on at the lower voltages. That's a little interesting aside. Probably warrants an investigation video. That's interesting. Anyway, it can actually still perform calculations. Let's do 69 factorial there. Oh, you can do it. Oh, there we go. It just did it. It just did it at 0.73. Oh, crazy. So I'm going to say the lowest we can, absolute lowest we can get this working at is 2 microamps at 0.75 volts. And 2 microamps times 0.75 volts, we're talking, 1.5 microwatts. There you go. So a calculator like this, ultra low power, custom ASIC design, it's, you know, you can actually do useful work at, you know, 1.5 microamps, a couple of microamps to actually do some useful work. But certainly you're not going to get anywhere near this with any sort of smartwatch. But as you saw, as the voltage went up, well, so does your current. So, you know, like, as I said, like 10 microamps, you can start doing, you know, useful kind of work. And for something resembling some sort of like wearable smartwatch type device, we've got the EFM32 Gecko processor here, really ultra low power stuff, and a graphical e-ink display, which you might find in a modern smartwatch. Of course, they take no power when you have a static image on them. They only take power when you actually update the information on them. Very cool technology. Well, what does this thing take? Just doing a simple clock like that. It's not doing anything. It's not transmitting, it's not, you know, sensing anything else. Well, there you go, in the order of 500 microamp pulses at 3 volts. So we're talking like, you know, 1.5 milliwatt peaks there. But of course, you know, in a typical product, of course, the actual energy harvesting device wouldn't actually supply this peak power. It's only got to supply the average power. That's when your decoupling capacitors actually handle the peaks and stuff like that. So you've got to have some sort of storage. So, you know, the average figure and stuff like that. But, you know, still, like just doing a basic clock like that, the process got to wake up from sleep every second. It's got to take, you know, gulp 500 microamps. It's got to update the, you know, the display and do stuff. And then when it's not taking those bursts of current, when it's down in sleep mode, yeah, you know, we're talking a couple of microamps. This is a typical sleep current of modern ultra low power micros. You can get like in the order of like half a microamp, you know, hundreds of nanoamps, but, you know, like in deep sleep. But then it's got to wake up and it's got to actually do something. So your averages have to be like much higher than that. So once again, multiply that by 3 volts and you got like, you know, 6 microwatts. You're approaching that 10 microwatts again before you can even do even the most rudimentary stuff. So anyway, I hope those measurements give you some sort of feel for what modern wearable devices, even ultra low power stuff that do something incredibly simple like this clock here, can take. You know, you need like tens of microwatts and then you start talking hundreds of microwatts before you start doing any smart stuff in quote marks. Yeah, it's just, God, and these things generate 100 nanowatts? Give me a break. So here's another graphic that they provide, and this is actual test results from actually putting it on your skin like that. Okay, so that's really cool. Yeah, they show, okay, 35 degrees, 35.8 for the skin. As I said, it's going to be a bit lower than your 37. Typically, that's your internal temperature, and you've got a 25 degree ambient thing. So a nice, realistic test. There's a thermal image of the prototype and stuff like that. And, well, what power output are we getting? Yeah, we're not even microwatts. We're in the order of nanowatts. We're talking 100 nanowatts. That's not even going to power the lowest power calculator, let alone a regular digital, like just a regular Casio, 1980s digital watch. It's not going to even power that. And then, interestingly, it looks like they get some data on the flex and stuff like that. So, this is actually really good research. It's great. I love the look. Then the thermal shots as they like bend it and stuff like that. Anyway, really cool. But you're starting to see that the hype actually from this paper that we're going to power the Internet of Things, the wearables, and everything else. No. Sorry, you're not even going to get the dumbest Casio watch powered from one of these things. And as I showed in my busted video here, that this power watch thing was just a gimmick, basically, is because, well, let's go take a look at a data sheet for a typical coin cell battery you would have in a wearable device like this. Okay, standard Energizer CR2032 battery. This is actually a bit bigger than you might have in some little slimline Casio watches. You might have a 1616 cell. If you don't know, by the way, this number actually tells you the size of the cell. The 20 here, actually, the first two digits here actually tell you the diameter in millimeters. It's 20 millimeters diameter. And the 32 here actually tell you, put a decimal point in there, and it's 3.2 millimeters thick. And so a CR1616 cell would be 16 millimeters across by 1.6 millimeters thick. There you go. Anyway, one of these coin cells, look at this, 235 milliamp hours down to 2 volts. That's basically, the characteristic curve. It just drops off right at 2 volts. Yeah, there's nothing left. Yeah, there's just like no energy left under that curve there at 2 volts. You've come a gutser. So what's the capacity of a 2032 coin cell in watt hours? Because we can't use milliwatt hours, because that's milliwatt hours. It's not watt hours, which is how you measure energy capacity and how we're comparing to this little thermoelectric generator as well. Well, 235 milliamp hours times, eyeball that. Let's say it's say 2.8 volts over its maximum life. I know you've got to integrate the whole thing, but yeah, near enough. So 235 milliamp hours times 2.8 volts, that's about 658 milliwatt hours. All right, so let's do some post-it note Dave calculations, shall we? Now, let's assume that this thing can generate its peak 10 microwatts. It can't, because you'd be dead due to the temperature differential, but let's, even though it's like really 100 nanowatts, let's just assume, be incredibly generous, it's 10 microwatts, okay? So how long can a CR2032 coin cell power a product at 10 microwatts? Well, okay, so we know that we've got 650 milliwatt hours here. We divide that by 10 microwatts. What does that give us? Get the confuser out. That's 65,000 hours. Yeah. 65,000 divided by 24 hours in a day, divided by 365 days in a year. We're talking over 7 years, 7.4 years. And that's actually a reasonable calculation, because really you can't get anything really useful under 10 microwatts, really. You might, a watch can get a bit under that, but like definitely not a smartwatch or any sort of modern Internet of Things wearable device. When you start talking about Bluetooth communication and stuff like that, even Bluetooth low energy, sending packets, and even if you've got an e-ink display and you're doing all sorts of other things, there's not much you can do in 10 microwatts. So that, is a realistic figure. So a typical wearable device, Internet of Things device, could be an order of magnitude or two greater than this 10 microwatts. And of course, this thing can only generate 100 nanowatts per square centimeter at typical room temperature on a skin. So come on, it's not no hope. Most people just toss their little Internet of Things wankery gadget out after 9 months anyway. Or the firmware update will brick the stupid thing, or they'll just discontinue support, or they'll start charging you bloody a monthly fee to use the damn thing. Otherwise it just disables itself and bricks itself. Bastards. You don't think that's real? That's actually happened. I'm sure I've done a video on that. Yes, I have. Anyone remember Sonos, who they deliberately brick their products? And you hear about it all the time. I think I just tweeted one the other day. Internet of Things bullshit. And here's how they've got like the Lego-like configuration and stuff, and how you can like just join them to, you can basically put them in series and get larger voltages out. But anyway, that 1 by 1 square centimeter, it's not going to do anything. It has no practical application for wearables at all, let alone charging smartphones and other rubbish like that. And I know you want to know how many of these little 1 square centimeter ring type devices it'd take to actually charge a smartphone in 1 hour. Well, typical 5 watt hour battery, they might be bigger than that, but you know, let's run with it. 5 watt hour battery in your smartphone to recharge that, assuming the phone's not used at all, in 1 hour, and assuming that your little doodaddy thermoelectric generator ring thing can actually get out the 10 microwatts absolute maximum that it claims, and you're dead anyway because it's, you know, there's 95-degree temperature difference, but just ignore that, right? 10 microwatts, we're talking you need 500,000 of these devices plastered all over your body with a 95-degree temperature differential to, like, you're dead. So you're like standing on Mars or something. That's where you get a temperature differential that big. You would need 500,000 of these to plaster your body to actually do that. So that's a big yeah, nah. So hopefully you're starting to understand the practicality of these sort of things, and how this is just, it's just hyperbolic, impractical rubbish that they're doing here, based on like probably really good and important research that'll have, you know, niche, these things aren't useless, they will have niche applications, but putting them on your skin is not one of them. I can't really think of any practical application where having a bunch of these things on your skin, even with a, you know, a decent temperature differential, you'd have to be pretty cold, as we saw in those performance curves, to get even like the absolute maximum out of 1 square centimeter is 10 microwatts. And that's just, you know, crazy. But in their practical tests here, it's in the order of nanowatts. It's like 100 nanowatts. It just, like there is an application for these in remote sensing applications, as there are with lots of these energy harvesting stuff, remote sensor, real ultra low power remote sensing applications. You might even have enough power to, you know, occasionally, you know, burst a bit of a Bluetooth low energy packet with some data back from a sensor, low power sensor, environmental sensor, or something like that, especially in places that are hard to reach, difficult to replace batteries and stuff like that. But otherwise, no, you're simply better off just sticking your coin cell. I know they're supposed to be, part of this thing is supposed to be, oh, environmental and battery waste and all that sort of thing, but realistically, like one of these batteries can last a couple of years in your watch. You can even like buy standard watches on the market that can get 10-year battery life, shelf life of the battery. They run off the smell of an oily electron. But that's only because batteries' chemical energy is incredibly dense. You just can't get this from energy harvesting. Just to get the equivalent from an energy harvesting device, like to get 235 milliamp hours equivalent to 1 coin cell, it's just, nah, it's just ridiculous. This is so impractical for all the stated applications. It's just never going to happen. So there you go. I hope you found that interesting and useful. If you did, please give it a big thumbs up. And as I said, do yourself a favor and go subscribe to Anton's channel, because it's absolutely fantastic. I watch every single one of the videos. It's great stuff. Really, you won't be disappointed. Catch you next time.